Greetings, AP Calculus students, to another day of our discussion in how derivatives can help us analyze functions in terms of their behaviors. In today's discussion, today's lesson, we will be looking at a topic called optimization problems, where we see a lot of applications of this idea of finding maximums and minimums. And this time around, though, a lot of the functions that we're going to be looking at are going to be functions in context. So many different types of application problems. But before we get to that, let's do our bell ringer as usual. Once again, please try it out on your own first before watching the solution. So we're asked to find two numbers whose sum is 20 and whose product is as large as possible, okay? So we're trying to find two numbers that add up to 20, but whose product is as large as possible. So I'm going to show two different techniques here. This might not be the technique you used, but I'm going to show two different techniques here. And both of these techniques are going to be non-calculus techniques. So they're going to be techniques that you should be able to do without knowing any calculus at all. So the first technique that we're going to discuss is this idea of just guessing and checking. Just literally trying out different combinations of numbers that add up to 20 and then just calculating their products. So let's say, for example, we picked 13 and 7. Okay, so 13 and 7. 13 plus 7 is equal to 20, and the product of these numbers, 13 times 7, is equal to 91. All right. Let's try a different combination. Let's try 15 and 5. All right, so 15 and 5, 15 and 5 both add up to 20. Their product this time around is 75. So it looks like that 13 and 7 seems to be in the lead. All right, let's try 19 and 11. I'm sorry, 19 and 11. 19 and 1. 19 and 1 add up to 20. And their product is 19. Okay, that's not even close to 91. Let us try 11 and 9. 11 plus 9 is 20. 11 times 9 is 99. Okay, let's try one more, which actually ends up being our answer. 10 times 10 is equal to 100. So you'll see that 10 and 10 are those two numbers that create the largest product, but that also add up to 20. So 10 and 10 would be our answers. So once again, you would have to try, obviously, a guess and check approach to get to this idea, but that is one technique you can use to solve this problem. So now let's use a technique that's a little bit more math intensive as opposed to just guessing and checking. And this one involves actually assigning some variables. So let's call our first number X. So that's our first number. And we'll call our second number Y. So this is what we're told about these two numbers. So we're told that X plus Y is equal to 20, right? X plus Y is equal to 20, and we're trying to find the product between these two numbers. So the product between these two numbers, X times Y. All right. Well, we're going to do a little trick here to turn this equation of X times Y into an equation of just one variable. So I'm going to rewrite this X plus Y is equal to 20 by subtracting both sides by X into 20 is equal to, 20. Y is equal to 20 minus X. So Y is equal to 20 minus X. So I just subtracted X from both sides, and I get Y is equal to 20 minus X. Well, now I can rewrite this product equation as X times 20 minus X, which gives us 20X minus X squared. So what's the relevance of this equation? Well, hopefully, if you remember back to Algebra 1, you would remember that this type of equation, since it's x squared, since the largest power is x squared, we call it quadratic. And if you recall, if we were to graph this quadratic, it would look like a parabola, right? So the graph of this, since there's a negative in front of this x squared, would look something like would look something like that, right? Now, since we're trying to find the product who's the largest product of these two numbers, in other words, we're trying to find the maximum of this parabola, the maximum of this parabola. And if you recall, the maximum of a parabola is also the vertex of that parabola, the vertex of that parabola. Well, there is a quick formula we can use to find the vertex of a parabola. The x value of that parabola we can find by doing negative b over 2a. Negative b over 2a. Now, what do b and a represent? B in this equation represents the coefficient of the x term, so 20. So b represents the coefficient of the x term, which is 20. And a represents the coefficient of the x squared term. We have that invisible 1 there, right? Since it has no coefficient, it means it's 1. So we get 2 times 1. Negative 1 times 2. So this gives us negative 20 times, divided by negative 2, which is positive 10. So there we go. That is the x-coordinate of our vertex, and that just happens to be our first number. Since our first number is 10, that means our second number, since they have to add up to 20, if our first number is 10, that means our second number would also have to be 10, right? Because if the first number is 10, right, x is the first number, and these two numbers have to add up to 20, the second number would have to be 10. So that's a little bit more math-intensive technique that you can use to solve a problem like this by using what we know about quadratics. And how the fact that the maximum of a parabola is that vertex of that graph. So once again, we didn't use any calculus, we didn't use any derivatives, nothing like the sort. We just use basically guessing and checking and some algebra 1 to figure out or to answer this question. This is one type of question that we're going to be going over today in terms of optimizing it by using derivatives, all right? So once again, I can use derivatives to solve optimization problems is our objective of the day. So let's first talk about what optimization is. So what is optimization? One of the most common applications of calculus involves the determination of minimum or maximum values. Consider how frequently you hear or read terms such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, greatest distance. Before outlining a general problem-solving strategy for such problems, let's look at an example. So you'll see this idea of optimization comes into play into a lot of areas outside of just pure calculus. For example, in financing, when we get to this idea of, or business and financing, when we get into this idea of greatest profit or least cost, or if we get into this idea of greatest voltage, optimum size, so manufacturing, physics, things like that, greatest strength, greatest distance, you might see something like that in things such as architecture. So definitely a lot of applications of these types of problems. Today we're going to go over a couple of more general optimization problems. Then over the next couple of lessons, we'll get into more, what's the word I'm looking for here? More subject-specific types of problems. For example, we're going to look at a couple of financing examples and so on and so forth. All right, so let's get our first example. So a manufacturer wants to design an open box, keyword open box, having a square base and a surface area of 108 square inches. What dimensions should the box be in order to produce a box with a maximum volume? So maximum volume. So we're trying to maximize the volume of this box. So that's the one key characteristic that you will see in all optimization problems, this idea of finding the maximum or minimum of something. So we're trying to maximize or minimize something. So in this case, we're trying to maximize the volume of this box. So right off the bat, let's write the equation down for the volume of this box. So volume equals, so if you recall, the volume of a three-dimensional object, in this case a three-dimensional or a rectangular prism, is just length times width times height. Well, the base, the length and width of this box is just x and x. So we have x, So we have x, oops, come on. So we have x times x, and then the height is just h. So that means the volume of this box is x squared times the height. All right, so we got that down, So once again, just length times width times height. Now we're also told that the surface area of this box is 108 square inches. So the surface area of this box is 108 square inches. So the next thing we're going to look at, is this idea of how do you find the surface area of this box? Well, if you recall, the surface area of a prism, such as this, would just be adding up the areas of each of the faces. So the area of this face, plus the area of this face, plus the area of the face in the back, plus the area of the face on the left side of this box, and plus the area of the face on the bottom. Now, once again, since it is an open box, this face does not exist on top, right? It's just open. So it's just an open box, so there is no surface area on top since there is no face there. All right, so let's see. So the area, so let's actually write down each of these. So surface area, come on. Nope, sorry. Stop being fidgety, come on. All right, nope. All right, there you go. So surface area. So the front of the box is just going to be x times h, right? So x times h. And now the back of the box is going to have the same area, or the face of the back of the box is going to have the same area, so x times h again. So plus x times h again. And now let's do the sides. So the side here is going to be x times h again. So the side is just going to be x times h again. And then there's going to be one on the left side of this box, so another x times h. And then the bottom face is going to be x times x. So x times x. And then once again, the top is just open, so there is no face there. So we're just gonna skip past that since there is no area there. So let's actually simplify this. So we have 4 xh's here. So I'm going to rewrite this as 4x times h. And then this is x times x. Come on. This is x times x. So x squared. Let me make sure something here. Oh, okay. Sorry about that. All right. Okay, just wanted to make sure it was still recording. I was afraid that it had stopped. But it looks like it still is. Okay, cool. Okay. Oops. So similar to the bell ringer problem, since remember we want to maximize this. Oh, I'm sorry, the surface area is 108, so this is equal to 108. So similar to the bell ringer problem, we want to maximize this. But unfortunately, it's an x squared and an h, right? An x squared and an h. So we're going to eliminate the h in this problem. By solving, by getting h by itself in this equation. So we're going to get h by itself and then substitute that in for the h in the volume problem. In the volume equation. So let's do that. So let's subtract both sides of the surface area equation by x squared. So we have 4xh is equal to 108 minus x squared. So 4xh is equal to 108 minus x squared. Now we're going to divide both sides by 4x. So divide by 4x. So h is equal to 108 minus x squared over 4x. So 108 minus x squared over 4x. We got that. All right. So now let's substitute. So once again, we're going to substitute this in to that equation. So now we got x squared times h is equal to 108 minus x squared over 4x. Okay, so just to highlight this. So remember, we took this and we substituted in for h which became that, right? So h became 108 minus x squared over 4x. Now we're going to simplify this a little bit to make it a little bit nicer for us. So let's see. We have an x squared times a quantity over 4x. So this x and this x cancel out. So now all we are left with is x times the quantity 108 minus x squared. Whoops, over 4. Darn it. Forgot the over 4. Okay. So now we're going to we're going to distribute the x into the terms inside the parentheses. So let's see, we got 108x minus x cubed. And then I'm going to rewrite that over 4 as just multiplication by 1/4. Okay, so if we divide by 4, that's just the same thing as multiplying it by 1/4. Okay, so remember, this is the volume equation, and we're trying to find the maximum volume. Now, recall, in order to find the maximum the maximum of a function, what we have to do is we have to take its derivative. So we're going to take the derivative of this equation. So let's do that. Now, the 1/4 is just a constant, so it doesn't bother us. So v prime. So the 108x just becomes 108. And the x cubed becomes 3x squared. Okay. So we took the derivative of the function that we want to find the maximum of. Now we set it equal to 0, because remember, those are the critical numbers where a maximum can occur. So at this point, once again, the 1/4 we don't really care about, so we want to make sure that we set 108 minus 3x squared is equal to 0. So let's solve this. So 108 is equal to 3x squared, just added 3x squared to both sides, and then divide both sides by 3. So 108 divided by 3, let's see, what is that, 36? So 36 is equal to x squared. So it looks like x is equal to plus or minus 6 if we take the square root of both sides. If we take the square root of both sides, we get plus or minus 6. Now, in a lot of these problems, you have to be careful. Once you get these critical numbers, once you get these x values, in this case, could be any other variable, but once you get your variable values, you want to make sure they make sense in the context of the problem. What I mean is, for this example, -6 would not make sense. Since we're talking about the dimensions of a box, for example, the length of a box can't be -6 units, right? Or in this case, -6 inches. So in this case, the only x value we actually care about is x is equal to 6. And that's the only one we're going to consider. Now, let's just make sure it is indeed a maximum. Let's indeed make sure that it is indeed a maximum, which, remember, we can do by just doing a simple number line test. So that's 6. So we're just going to test a value less than 6 and greater than 6. So less than 6, let's just test 0. And once again, I'm testing it in the derivative. Well, if I plug in 0 into the derivative, it just gives me a positive number. Now, if I plug in 7 into the derivative, you can just do the math, and you should get a negative derivative value. Hence, the maximum, we've verified that this is indeed a maximum, right? Because the graph is increasing since the derivative is positive. Then the graph starts decreasing, so it goes up, right? It goes up, then goes down. So that means there's a maximum up here. So that's just to make sure we indeed have a maximum. So now we're not done yet, because we're asked what the dimensions are. So we found the length and the width, right? We found the length and the width. So now we just got to find the height. We just got to quickly find the height to make sure we have satisfied this question. So, well, let's see. Well, we're told that the surface area 108 is going to be equal to 4 times 6 times the height plus 6 squared. So right now I'm using this equation. I'm using that surface area equation that we wrote previously. So I'm just using this equation and plugging in 6 for x. Just plugging in 6 for x to get h by itself. Now, whoops. Let's see. I could have sworn. Man, I forget sometimes. I could have sworn there was an undo button. Okay. So now we're just going to get h by itself. So let's see. 4 times 6 is 24. So 108 is equal to 24h plus 36. Subtract 36 from both sides. 72 is equal to 24h. Divide both sides by 24, so h is equal to 3. So it looks like the dimensions of this box, if we were to just write them all out, would be a 6 by 6 by 3 box. So that is the dimensions of this box. So the length is 6, the width is 6, the height is 3. So these dimensions would maximize the volume of this box for this manufacturer, making sure to maximize the volume of this box. So that is one typical example of what an optimization problem would look like, okay? So you'll see it's not, in reality, the concepts that we're covering, even in this first example that we did, there isn't much anything new to it. For example, this idea of just finding the maximum of a function equation by finding its derivative and then setting it equal to 0 is nothing new. We've done it many times before. The more the more new aspects of this idea of optimization is just the fact that we start with two formulas and then we have to somehow figure out how to use these two equations so that we can ultimately reach our goal. So before we look at example 2, let's just go over some of the common steps that you would follow or the common strategies that you would follow whenever you have an optimization problem before you. Okay? So number 1, identify all given quantities and quantities to be determined. If helpful, make a sketch. So sometimes drawing a picture can be helpful, not necessarily. I mean, one thing definitely is helpful. In this first example, we were already given a picture. One thing, especially if you're not given a picture, is just making sure you identify what each of your variables means. Since we were given a picture in this problem, our variables were basically defined for us already. X was the length and the width, h was the height. So just something that you want to consider in case a picture is not provided for you. Step 2, write a primary equation for the quantity to be maximized or minimized. So in our example problem that we just did, that was the volume equation. So the volume equation was the equation that we want to maximize. So you always want to make sure you identify what equation you are maximizing or minimizing. Now, in optimization problems, it's typically very obvious which equation you want to maximize or minimize because they tell you the quantity that you want to maximize or minimize in the problem, right? It told us to maximize the volume, so we want to maximize or find the maximum of the volume equation. Step 3, reduce the primary equation to one having a single independent variable. So, excuse me. So ultimately you saw in our volume equation, it was in terms of two variables, right? X and H. X and H. Ultimately, we used a second equation, which we identified by the fact that it told us the surface area was 108 square inches, so that we can isolate a variable, right? In this case, we isolated H so that we can plug it back in to our primary equation, right? The equation that we want to maximize, so that we could only have one variable in the end. And the reason we only want one variable in the end is because remember, since we're trying to find the maximum of that equation, we want to take the derivative of that equation. In order to take the derivative of that equation, we got to be able to write that equation in terms of just one variable. Then step 4, determine a feasible domain for your primary equation. So this is something you typically do on the fly. You wouldn't do like in a separate step. So for example, for us, we only did it once we found those x values, right? We found x to be plus or minus 6. And then we just eliminated the negative 6 because it wouldn't make any sense in the context of the problem for our length and our width to be negative. And then finally, step 5, determine the desired maximum or minimum value, taking the derivative, finding critical numbers. And then just making sure, like we verified that our x value was indeed a maximum by just doing the number line test. You can also do the second derivative test if you remember that test where you find the second derivative and see if it's positive or negative from there. So you could also do that too. So let's look at another example. So which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So our closest So this idea of being close. So we got to ask ourselves, what are we trying to minimize, right? If you're trying to find something that's close, what you're trying to minimize distance. You're trying to minimize distance here, and that's what we're trying to do. So we're trying to minimize distance in this problem. So, let me just make sure here. Is it still recording? Oh, sorry. Yeah, it's still recording. Okay, just wanted to make sure. Okay. We did all that. Sorry about that. Okay. All right. So, distance equation. Does anybody remember about the distance? How do you find the distance between 2 points? So this is something should have been covered in geometry, might have been talked about in Algebra 1, this idea of finding the distance between 2 points. To find the distance between 2 points, please go back. Okay, to find the distance between 2 points, you use the following equation. Distance is equal to the square root of x2 minus x1 squared plus the quantity y2 minus y1 squared. And it's just a derivative. It's derived from the Pythagorean theorem. It's just a squared plus b squared is equal to c squared. Basically, that's all this formula ultimately comes down to. So that is how you find the distance between 2 points. All right. So we're trying to find the distance between a point on the graph, y is equal to 4 minus x squared, which I'm just going to quickly graph here. So it has a y-intercept of 4, x-intercepts of negative 2 and 2. So our graph looks something like this. Ooh, that's a terrible curve. Okay, sorry about that. And the point 0, 2. So we're trying to figure out what point on this parabola is closest to this point 0, 2. So that's what we're going to do. Okay, so let's see. Well, x2 and x1. So let's make this our x2. Actually, let's make this our x1. Doesn't really matter, actually. The order doesn't matter. We're going to make that our x1. Well, what's our x2? It is a point on this curve, right? It is a point on this curve. Well, we don't know where on this curve it is, but we know it's an x value, right? So our x2 is actually just going to be x. We know it's an x value. So we know it's an x value on this curve. 2 is going to be our y1. What is going to be our y2 for this problem? Well, our y2, since the y value is determined by this graph, our y2 is just going to be this equation, 4 minus x squared. Because the y value of this graph, all the y values on this graph are determined by 4 minus x squared. So our y2 is just going to be 4 minus x squared. So now we're just going to plug this all in. So the distance is equal to the square root. So let's see, x2 is x. x1 is 0 squared. Plus y2 is 4 minus x squared. Y1 is 2. Okay, so I just did, right, x1 is 0, y1 is 2. So x1 is 0, y1 is 2, x2 is x, and y2 is 4 minus x squared. So let's simplify this. So x minus 0 is just 0. I'm sorry, x minus 0 is just x. So it looks like what we have here is x squared. Let's see, 4 minus x squared minus 2. So 4 minus 2 is 2. So it looks like, sorry about that. So we got 2 minus x squared squared. So we got to simplify that. We're going to simplify that. Let's do that off to the side. So we're going to simplify this 2 minus x squared. So remember, 2 minus x squared is just the same thing as 2 minus x squared times 2 minus x squared. So we're going to distribute, or as many of you call it, foiling. So let's see, we get 4 minus 2x squared minus 2x squared plus x to the 4th. So 4 minus 4x squared plus x to the 4th. All right. I can rewrite it here. So it looks like what we have is the square root of x squared plus 4 minus 4x squared plus x to the fourth. So it looks like we have some like terms here, x squared minus 4x squared, so 1x squared minus 4x squared, so that's negative 3x squared. So square root negative 3x squared plus 4 plus x to the fourth. Okay, so that's as much simplifying that we can do. There are no more other like terms. So we only have a single variable, so we're good there. We only have a single variable. We don't have to do any more substitution here. Now remember, since we're trying to minimize the distance, find the minimum of the distance, now we want to take the derivative. Oh my gosh, calm down. Now I'm going to take the derivative of this. So I'm going to rewrite this as, remember when you take the square root of something, it's just taking it to the 1/2 power. So x to the fourth minus 3x squared plus 4 to the 1/2 power. So we got to use the power rule for this and the chain rule. So let's see. So we end up with 1/2 times the quantity, so this is d prime, 1/2 times the quantity, x to the fourth minus 3x squared plus 4 to the negative 1/2 power times the quantity in the inside of times the derivative of the inside, so 4x cubed minus 6x. So 4x cubed minus 6x. So we got that. So remember, we're trying to find when this is equal to 0. So when this is equal to 0. So the only quantity that we actually care about this actually can never equal to 0. You can easily verify it by just graphing it. So this can never equal to 0. So the only part of this that we care about is this 4x cubed minus 6x. So we're going to set that equal to 0. So 4x cubed minus 6x is equal to 0. So it looks like we can factor out a common factor of 2x. So let's do that. So 2x squared minus 3 equal to 0. So it looks like x can be equal to 0. X can be equal to 0. Right? We can set 2x is equal to 0 and 2x squared minus 3 is equal to 0. So x is equal to 0 and 2x squared is equal to 3. Divide both sides by 2. X squared is equal to 3/2. So it looks like x can be equal to plus or minus the square root of 3/2. Now this time around, since we're not talking about the dimensions of a box, our x value can be negative. There is no issues with our x value being negative. Our x value can be negative, so we have no issues there. So now I have to do the number line. Now it looks like I'm trying to run out of some room here, so I might have to erase some things. Let's erase, I want to do a number line here, so I'm going to erase these here. Come on. No, oh no, it got stuck there because of, all right, let's see, what could I do here? Oh, this is going to be messy. Okay, I got an idea. I have some room left. There you go, I got some room left up here in the corner. All right, so we have 0 and then plus or minus radical 3 over 2. So negative radical 3 over 2, 0, and then positive radical 3 over 2. Okay. So let's test out some values. So let's see. Radical 3 over 2, if you quickly plug that into a calculator, so radical 3 divided by 2 is 1.22. So that means since radical 3 over 2 is 1.22, that means we can test 1. So if we test 1 in the derivative, so derivative is this one. So let's see, we get 1 minus 3, negative 2 plus 4. So that's positive. 4 minus 6, that's negative. So it looks like we're going to have a positive times a negative. So that's negative. Right? So now let's test 2. Since, remember, this is 1.22. So let's test 2. So let's see if we can do some quick math here. So this actually ends up always being positive. So you actually don't have to worry about, I mean, you can do it. 2 to the 4th is 16. minus 3 times 8, so that's 24. Or wait a second. Plus 4. That doesn't make any sense. Huh? 16. Oh, whoops, 2 to the 4th. Whoops. 3 times 4 is 12. So plus 4, so that's positive. Sorry about that. So it would be 16 minus 12 plus 4. So that's positive. And this ends up being, let's see. So we're plugging in 2. So 8 times 4, 32 minus 12. So that's positive. So we get a positive, positive. So that's positive. Now let's try negative 1. So this is negative 1.22. So between that, we try like negative 1 here. So once again, this is always positive. Don't worry about that. So we get negative 4 plus 6. So that's positive. Negative 4 plus 6 is positive. Okay, so we got that. And then finally, let's try negative 2. Once again, since this is negative 1.22, negative 2 would work. So this is always positive. So let's see what we got here. So we got negative 32 plus 12. So negative 32 plus 12. So that's still negative. So there you go. So once again, since we're minimizing, what are we looking for? Well, we're looking for the x values or the critical numbers. Remember, these x values are critical numbers where the derivative is equal to 0. Where the derivative goes from negative to positive, right? Decreases that increase. So it looks like it actually happens at 2 spots. Negative radical 3 over 2, negative radical 3 over 2, and then radical 3 over 2. So negative radical 3 over 2, and then positive radical 3 over 2, right? Negative, positive, negative, positive. So those are our x values. It's not 0 because 0 actually ends up being a maximum, so we don't want that. We want to find the closest. So at this point, we just have to find the y values. Now that's actually not too bad. So if you were to plug in these into 4 minus x squared, let's see, where can I do it? Running out of space here. Let me do it in a different color so it stands out better. There you go. So we just got to find the y values now. So 4 minus radical 3, radical 3 over 2 squared. So the radical and the square just cancel out. So 4 minus 3 halves. Well, 4 is just the same thing as 8 over 2. So 8 over 2 minus 3 halves. So 5 halves. And you get the exact same y value if you tried negative radical 3 over 2, since the squared would just take out the negative. So it looks like our two answers, let me use it in blue, our two answers are positive radical 3 over 2, comma 5 halves, and then negative radical 3 over 2, comma 5 halves. So at those 2 points, those are the 2 points on this graph that are closest to 0, comma 2. I think it ends up being somewhere here, if I recall. It ends up being like somewhere in this region. Those are the 2 closest points on this graph to 0, comma 2. Okay, so that's it for our lesson on optimization. I will be also posting a little bit extra practice on these types of problems that you guys can try out for a little bit of extra credit as usual. So I'll be posting those along with this lesson. So this is just our first day of optimization. Well, I think we'll have at least 2 more lessons on just more different types of problems, but on the same idea. Once again, identifying what equation you want to optimize, identifying a second equation just in case that first equation is in terms of more than one variable, so that we can substitute. Remember in that first example that we did, our equation was in terms of x and h. We have to get rid of that h. And then finding the derivative of the equation that we want to maximize or minimize. In this case, we were minimizing the distance. And then just finding the critical numbers and just verifying that what you have are indeed maximums or minimums, respectively. So once again, hopefully this first day of optimization went smoothly. Once again, it's not too much new calculus. And we're just applying it a little bit differently. I mean, we found maximums and minimums of functions before. It's just that in some of these problems, we have more than one equation that we have to deal with. Well, as usual, people, I hope you guys are staying safe. I hope you guys are staying healthy. And otherwise, hope you guys enjoy the rest of your days. See you later.